So we are resuming our sessions. I was away for 2 sessions on, I think, again Thursday and Saturday. I went through a bout of COVID Omicron. So now I'm fine. So we are back. Okay. So so we will start and continue. Now, what all we have finished till date is we have finished looking at graphs. We have finished we have finished lists. We have finished trees. We have finished graphs, and now we are getting into strings. We have just 2 algorithms which we need to cover in strings. One is called the KMP, and the other is this is called Knuth-Morris-Pratt algorithm, and the second is called the Boyer-Moore algorithm for string comparison. Okay, so we are going to do the 2 algorithms, and KMP is a classic algorithm for pattern matching, and we are going to understand what is a KMP algorithm. We are going to look at a few examples and then understand. That's one thing we are going to do, and I think what is the second one? We have to integrate it with the database, right? User login. Okay, some application. So we'll see once we are done with this. Okay, with the Flask. Okay, so let me start with the KMP algorithm. But before that, let's talk about the problem, and then let's talk about where these algorithms comes from. Okay. Okay. The basic thing comes from is this. You have a long string. Okay. This is your long string, and you have a pattern. Some pattern, let's call it P, okay, and this is a string. Now you have to detect whether this pattern occurs in this string or not, whether this pattern occurs in this string or not, and if it occurs, I think you have to tell at what position it occurs. That is secondary, but first whether this pattern occurs in this string or not, that is called a pattern matching. There are many applications where we need it. One of the immediate application which comes to my mind is this. You are given a big gene sequence consisting of A, T, C, G. Now I think you know this A, T, C, G, the gene pattern. What is A? Let's see. What is A? A, what is T, what is C, and what is G? Okay, this is your DNA sequence consisting of a series of DNA sequence patterns, and it consists of ATCG. I'm just asking out of curiosity, what is A? Okay, adenine, correct. What is T? Okay, good. Somebody got it right. So it is adenine, thymine, guanine, and cytosine. Good. So these are the amino acids which make up the chain and which are used for creating our DNA. Right? Okay. So now I'm not going into the structure of this. Now very often one of the problem in bioinformatics is that the sequence is almost a billion pairs. So there is a billion long sequence, okay, or maybe more than many billion long sequence. So you have a billion long sequence, and in that sequence you want to spot a particular gene pattern which is this big. So when you want to spot this, algorithms like KMP will come in useful rather than the brute force or naive algorithm. Brute force algorithm is also called the naive algorithm. So rather than using, we will first see what is a brute force algorithm. That is fairly easy to see. And how does KMP improve? But KMP is useful only when the pattern consists of a limited alphabet. Limited alphabet. Now, that is excellent for DNA because the alphabet is really limited. The alphabet is only 4 characters. A, T, C, G. And it's repetitions of this A, T, C, G again and again, which basically create the DNA. So if you are looking for a particular pattern of ATCGs into a long DNA strand, then KMP like algorithm which work on limited alphabets are very useful. But if I didn't have this algorithm, what would be my crude or brute force approach? How would I do it? So I have this original DNA sequence, and here is the gene that I am looking for, which is a pattern of ATCGs. What I would do is, I would first compare it with this. If there is a match, good. If there is not a match, then I would go to I equal to 0, then I equal to 1, then I would compare this with this. If this is also not matching, then I would compare this with this. Okay. Like this, I would keep on going. So for each position of I would have to do these many comparisons. So if the length of this is n and the length of the pattern, gene pattern, is m, the length of the DNA strand, this is the DNA strand, is n, and the length of the gene pattern that I am looking for is m. For each position, I have to do maybe potentially m comparisons to check whether there is a match or not. So the complexity of that algorithm will be O and M. I hope you understand when I say O and M, that is, this is n times, and for each position I have to check so many times whether this matches or not. And I can write a very nice loop for it. So the loop will always start from, so the loop will be from I to n, and j will be going from I plus 1 to I plus m, something like that. We will compare each one of them. If any one mismatch is there, if any character mismatch is there, if DNA of I is not equal to gene of J, okay, this is the gene and this is the DNA. If it is not equal to that, then I will have to say break, and I will have to then go on forward. If I come out of the loop with no break, I will have to set some flag. If the flag is not set, so flag will be here equal to 0, and then I will set the flag every time. When I do a break, I will make flag equal to 1. Then if I come out of the inner for with flag equal to 1, that means I have an anomaly. Or if I come out with flag equal to 0, that means I found a match equal to 0. Then I equal 0. Then match. Okay. Anyway, you know what I am trying to do. So I am going through each position of I. With each position I am comparing this gene. So this is what is a naive algorithm. Okay. So I am sure you can write a naive algorithm, right? I mean, does this make sense to you? I am going from I equal to 1 to n, and for each position of I am comparing j is equal to I plus 1 to I plus 1 or I plus 0, right? To I plus m minus 1 maybe. M being the length of the gene pattern. So I am comparing it, and once I compare, if it is not equal, I set the flag equal to 1 and break. If flag equal 0 after the inner for loop, that means there is a match and I can say that, else I go back and try with the next position of I. Now again I repeat this and see whether I am matching appropriately. Now as I said, the complexity of this is O and M, that is for n times this loop has to execute. For each n this has to execute m times, m being the size of the G. Okay, so I have to do this. So this is an O and M complexity. Okay, is everybody clear? This is O and M complexity. Okay, can we check the chat? Yeah. So everybody is convinced it's an naive algorithm will give me an O and M complexity. Yeah. No, did you understand? We will have O and M complexity. Okay. Now it's going to be very slow. So all of that. Now instead of using that NM complexity, we can do it differently. We can improve it. Now how do we improve it? Okay, let's see how we can improve it. So that is where one of the algorithms is KMP. Now I will first talk about the KMP algorithm, then we will look at an example and okay, so let's go back to our okay. So let me first talk about the the intuition behind the KMP algorithm of string matching, and then we will go forward. Okay. So as usual, this is your given pattern, given string of length n, and your given pattern is of length m. Okay. This is of length n and this is of length m. Now, imagine that in M, now you'll have to think a bit about M. Imagine a pattern M is such a way that a lot of the suffix of the M also is there in the prefix. Okay. Now, this will take a little few minutes to understand. What do you mean by suffix? This is called suffix. This is called prefix. Okay. Now, if the prefix and suffix for this pattern are somewhat same to a certain extent. So let's say this is AT, CG, and again it is AT. This is the suffix, this is the prefix. To a certain extent you can see the suffix is similar to prefix. These two are similar to the prefix. And now let's take a pattern. Okay. Let's take a string pattern. Okay. And let's see part of the string pattern. Okay. Now let's say I will say somewhere in the string there is A, T, C, G, and let's say G. Okay. Yeah. So now, and let's say there is C, G, C something. Okay. Now I am comparing. When I started comparing, I have done comparison. Let's say my comparison is like this: A, T, C, G. So far, my pattern is compared. Exactly. This is my DNA, and this is my gene. Huh? Let it. So this has matched so far. Okay. Now, in the gene, that is in the pattern, I have A here, whereas here I have G. I have A here in the pattern and G here. So if you see here, AT. Now, what I can do, now this is a point of mismatch. This is a mismatch. There is a mismatch which has occurred here. Now, the peculiarity of my pattern is, now should I start matching again from the beginning? That is now, see, so far it has matched, till this point it has matched, right? It has matched up to this. Here there is a match. Up to here there is a match. Now, should I again start matching this where the point of mismatch is there? Should I start matching this again from here? Okay. That is, my I is here. Should I, this much has matched. Okay. Now there is a point of mismatch. Should I start matching it here, or can I do something better? That is, now I should start matching from I to j equal to 0 again. That is a new position of I. And should I now retrace the position of j to here? Because now it has not matched. This has all matched. So now should I compare I with A again? Because now mismatch has started here. So I can start going back here and start doing the comparison. That is, instead of, so now that there is a mismatch, again the pattern has to start from beginning. The mismatching or matching has to start from beginning. Now I have to take this I and matching with this A. Should I do that? Or can I do a little better? Okay, can I do a little better? Which means, can I skip some of this pattern to check whether there is a mismatch or not? Now here, absolutely there is no prefix concept. Okay, so here there is no other option, but I have to start from here. Okay, but now take a slightly different pattern. So in this case, I have no other more option but to again start matching G with A and proceed. But take a slightly different example. So in your string, this string, that is the DNA, something like this is there. A, T, C, G. Again, A, T is there. Okay. And again, let's say C is there. Okay. And, okay, no, let me draw it again. Let me draw a pattern and imagine you are at some part of the matching. So there is A, T, T again, G, T, again A, again T, again G, okay. And it goes on, dot 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 dot, and this is also dot dot dot. Okay, now think a little and let's say the pattern that I have with me is A, T, T, G, T, AT, let's say AT, G. No, AT. This is my pattern. Okay. Now, and now I have, let's say, AT, C. Okay. This is my pattern. This is the DNA. This is the G. Now, watch it carefully. Eh? Now I am matching. I am at position I. So this is my I. Okay. And this is my G. I am matching. So far now it has not matched. I matches. Okay. So this has matched. This has also matched. So this has also matched. This has also matched. Okay. This has also matched. This has also matched. Now I got a G and here I have a C. So this is the point of mismatch. I will say this is the point of mismatch. Now, when you get a point of mismatch, what needs to happen? Now, if I am following the naive pattern, so I am I is here and J is here. Okay. So now what I'll do, I have a mismatch here. So again, now the whole thing is not matched. So I can start with this value of I or any given value of I. The question is not about the value of I, the question of value of J. From where should I start matching? Now, here there has been a mismatch. That means the earlier part has matched. Okay. So, should I start matching J from the beginning? That is again match this J with this A and all of that. Should I start matching it from there again? Because the point of mismatch is there. So should I start matching it from here, or since this much has already matched, okay? So obviously it doesn't match, but if this is matching, now should I start from here, from the beginning? That is, should, when mismatch happens, mismatch has happened, should J go to 0 again, or can I do better? Okay, should J go to 0 for the next check? Now I again have to start from here. But if you look at this pattern carefully, you see this is a suffix of the pattern which has matched so far. This portion has matched so far, this to here. Only then did we come here, no? So this has matched. In the matched portion of the pattern, till here whatever is there, this is the prefix, suffix. This is the suffix. That suffix is also a prefix. Okay. So the fact is, if you look back, I don't have to start, these two are already matched, because if you see, this portion has matched. In the portion this has matched, the suffix is also the prefix. This suffix is also the prefix. It exists that way. Because it exists that way, yeah, then I can start the matching not from beginning but from here. Because you see, this is already matched and this is also the prefix here. This is the suffix of the matched portion. See, this is the complete matched portion so far. This is the suffix of the matched portion. The suffix of the matched portion is what? AT, which is also in the prefix. So, instead of starting at J equal to 0, I can start at J equal to 0, 1, 2. I can start at J equal to 2. Because I can say that there is no need to match this AT again here. It has already matched. Now I can say, I can check whether G matches with T. Okay. So suppose there is a T here, we can match whether that is matching already with this, or if there is a C here, we can see that there is a matching here directly or not. Okay, so you can say if there is a G here, you can see that directly there is a matching here or not. You can jump not to the beginning of J. You don't have to go to J equal to 0. You can start with J equal to 2. Why is this possible? Because there is a suffix in the match portion which is equal to prefix. This has already matched. Okay, this is already matched. Because when you have this mismatch happening here, see, this portion is already matched and that is there in the prefix, so you can ignore this. Because in the suffix, this, it's also repeated here and you can start matching from here. Okay, what it means in a general sense is this. Okay, suppose there is a bit of string from here to here, okay, which you are worrying with the matching, and let's say this is pretty long, and till this point now you have a pattern which you are trying to match. This is the portion of the string, original string, the DNA. I am calling it this as the gene which you need to match there. So if this portion, and this is the point of mismatch, okay, this is where mismatch happened between this and this. So in this case, let's say this is the position of mismatch. This is same. Till here it has matched. Okay. Now this is the position of mismatch. So this is the I here and this is the J here. So this is the position of mismatch. But the pattern looking back from J is such in your gene pattern. Let's say these characters and these characters are same. That is, this prefix and this suffix is the same. Then till here it has matched. What it means? It means that if you see this is the position of mismatch, this suffix has already matched, okay, which is a prefix here. So why should I start? This has already matched. So because there is this suffix and prefix are same, this and this, that is a peculiarity of this pattern, let's say, which is very common in gene mapping, that this pattern may be in the end also, in the beginning also. So because this pattern is in the beginning and the end and it has matched so far, that means this suffix match which has happened can now be treated, because this is also occurring in the prefix, it can be treated as this has already matched, this portion has already matched. Now the matching can be tried from this J onwards, for this I. This portion can be tried from this position onwards, because there is no point in trying this portion again, because this portion is already there in the suffix which has matched. So if this is ATG and this is ATG, then this must be ATG because it has matched so far. So now I can start from matching this portion onwards. So I can start comparing this location, which is not J equal to 0, not J equal to 0, J equal to 0 is this, whereas this is, let's say, J equal to M, some location, not M, maybe some X, where this suffix and prefix are different. So till this point, whatever is there in the suffix is also there in the prefix. So whatever is the length of the suffix, I can subtract that length from this J and start from here, okay, rather than starting from here. Otherwise I would have to start matching from here, but the pattern which is getting matched is such that this suffix and this prefix are same. That's what I am indicating here. This is the suffix and this is the prefix. They are the same. Because they are the same and mismatched occurred at this position, that means this has already matched. So can I not skip this prefix matching of the original pattern and start matching from this to this? So I am reducing the number of matches which I have to do in my pattern, and if my pattern is very big, see, typically your DNA may be 1 billion long, your gene may be a 1 million long. I think you need to understand it so as to understand its impact. So if you can skip some of that, let's say 500,000 or something, that many comparisons will reduce and your algorithm will be that much optimized. Again, you can always argue that this will be useful only if the suffix and the prefixes are same. Otherwise it's of no use because it will not give any optimization. Yes, that is correct, and that is true often in case of genes where the starting codon, or what you call the starting ATCG pairs and the ending pairs are largely same, quite often same. So this can be used very effectively in those kind of situations where the suffix and prefix is same. Only when that is there that we need this to happen. So the argument is very simple. If I didn't have this idea that there was a suffix in my pattern before the position of mismatch, and there was a prefix which was exactly that, and I could skip the prefix match because the suffix has matched up to this point, then you have the argument that I can start the matching from here and save some matching. I can start the matching from here with this I rather than going back in the beginning and again trying the match. Okay, so that is the mistake which I mean that is the optimization which the Knuth, Morris, Pratt offers us. But to appreciate that, you have to see what is happening and do it. The algorithm is very simple. It is, you do I and j, and basically you have to compute this prefix suffix story and create this kind of do some pre-computation on this and keep the prefix suffix matches. I'll come to that. How do you do it with an example? But I think you should understand how to do this. So you have to understand the argument as to why KMP will be useful, what circumstances KMP is used. Okay, so I'll pause here. Let's see whether you are with me. Are you getting this prefix suffix story? Okay. Yeah, you may use 2 pointers but not 2 pointers either. You need to have a prefix story and you need a suffix. So in your original pattern which you are trying to match, imagine there is a prefix and imagine there is a suffix. So rather than matching the whole pattern, whenever there is a mismatch, you don't start the next part from the beginning, you start it from certain position ahead. Okay, so now does it make sense? Okay, to some of you it makes sense. Okay, let's try whether we get a better response looking at an example. Okay, let's look at a PPT example to see how it works. Okay, so we are now going to discuss more formally the KMP. So the Knuth, Morris, Pratt algorithm looks for the pattern in a text from left to right order, but it shifts. It is like a brute force only, but it shifts the pattern more intelligently than the brute force algorithm. Okay, now let's understand what it means by that. Okay, now if a mismatch occurs between the text and pattern at P and pattern P at Pj, so at that particular, sorry, go back. So the mismatch occurred at that. What is the most we can shift the pattern to avoid wasteful comparison? So the trick is to avoid wasteful comparisons in the pattern. The answer is the largest prefix in that range just before for 0 to pj minus 1, that is also the suffix from 1 to pj minus 1. So you'll understand what it means the moment I look at an example. Okay, now watch carefully what we are doing and what we are talking about. Okay, now focus your attention here. This is the text. Sorry, go back. Okay. So this is the text and this is the pattern you are matching in the text. Now understand the argument. Say whatever has happened before or later, don't worry. Now see what happened. Here A matched with A, B matched with B, this A matched with this A, this match A matched with this A, this B matched with this A. Now in the given text there is an X here and there is a A here. So this is called the point of mismatch. Now ordinarily what we would do, we would again start matching X with A, then B, then A again, like this. We would start matching whatever is coming here with here, right? And check. But now, do we need to match that at all? Now, from where should we start matching the J? Okay, with X. Where should we start matching? Now, the trick is, should you start again at J equal to 0, or because if this is the point at which mismatch happened and it so happens that this is the suffix which is matching with the prefix, so what it means that this AB has already matched because it's also there in the prefix which is also there in the suffix of the string. So if I start matching from here and wherever, and I again start matching with X with AB, it is meaningless. That is, this AB with this AB, I again, because this is a point of mismatch, I again go back. So this is deemed to have matched. Okay, and since it's in the suffix, now this is deemed as matched. So I should compare this X now from here. So X should be compared with A, not with this A. There is meaningless, no, because this AB, which is the point of mismatch, if you see in the pattern, this is repeated here also. So when the mismatch happened here in J equal to this, then you can skip these two positions and start mapping from here, because these two are matched, and you can start matching from here. You don't have to go back, this is already matched. So you can start matching this X with A and see whether you can get a match forward. Of course, in this case you won't get a match, that's a different issue. But this is deemed as matched because if you see my pattern, at this point, these two, this is a suffix, is same as prefix. So as of this, what is the length of the prefix which is same as suffix? These two. So I can skip these two in the beginning and start matching this with this, because these two are matched already. And the pattern is such that there is a prefix which is also there is a suffix which is also a prefix. So I can start matching from here and see whether that thing works forward. So these two comparisons, there is no need to repeat. Now I can compare only these four with whatever is there here when there is a mismatch. Now there is a match here or not, doesn't matter. So this saves us I from going back, I doesn't have to go back, and J again doesn't have to go back to 0, J can start from here. Okay, so the mismatch position, from this mismatch position in the pattern, I can subtract this prefix, this suffix which is matched already with the prefix. I can go only that many positions back and start. So I can do J minus 1 minus this, whatever is the length of the prefix which has matched, that is 2. So I can start at J equal to 2. So J is 5 at the point of mismatch. So this much has matched. So from that portion which is matched, I can deduct the length of the longest suffix which is also a prefix. The longest suffix which is also a prefix. I can deduct that because that is deemed as matched. And I can start the matching from this point onwards. See this, A, B, A. It is starting from that point onwards. Not from this AB. This is already deemed as matched. So it reduces the comparisons. First of all, I doesn't have to go back. And in this, the J has to only go back not up to 0, but subtract from the J minus 1th position the length of the longest prefix which is also a suffix, which is 2. So you go back and start comparing from here. Okay. So that is the secret of the algorithm, that you are not going back in I because that's matched already, and you are now continuing the match from this point onwards. Now if there is a mismatch or not, that is a later day story. Okay. So let's try and see whether we will follow this through. Okay. Okay. Now for this string, we have to build this prefix array or whatever it is called. We have to build this special array and then work with it. So how do you? Largest prefix which is also a suffix, or you can say, yeah, largest suffix which is also a prefix. Okay, either way. So we have to set this. Okay. Now there is a algorithm to do that, and we'll do that in a thing. So okay. Now how does KMP work? So there is a bit of pre-processing which KMP does. Pre-processing means the pattern is pre-computed. We do something to the pattern to ensure that we know whether how much of the prefix is same as suffix and all of that. So KMP pre-processes the pattern to find the matches of the prefixes of the pattern with the pattern itself. What are the prefixes of the pattern which are matching with the suffix? J will be the mismatch position in P. So the position before the mismatch, J minus 1. Now the failure function is defined as the size of the largest prefix of 0 to k, that is also a suffix of 1 to k. Okay, I'll explain what that means with the picture. This will take a little while to understand, but it's worthwhile trying to understand. Okay. Now, this is called the pre-computation. This is f of k. This is called the failure function. This is computed and kept. Okay, how is it computed? Now, look at this. Okay. Let's try and follow this. So this is the pattern. These are the positions in the pattern. Okay. So this is A. This is, I guess, A, B, A. No. Okay, sorry. The pattern starts here. A, B, A, B, A. Okay. So now we start from 1. This starts from 0 and this starts from 1. Now just look at these two first. The suffix is B and prefix is A. Just look at these two. Is there a prefix which matches the suffix? No, nothing. Okay. So we record 0 here. For the first 0, A, we have to record a 0 anyway. For the second position also we record a 0. Now look at this position. That is here. Look at this position. Just see up to this point, including this point. is there a suffix which is also a prefix? Yes. A and A is a prefix. A is a suffix which is also a prefix. Look at just this. Look at ABA. This is the suffix. It is also the prefix. So what is the length of the longest prefix which is also a suffix? Like this, only 1. So we record 1 here. Okay. Then look at this position. Okay. That is J3. Look at this. Now, what is the length of the longest prefix? Sorry, longest suffix which is also a prefix? A. Yes. So 1. Can 2 be there? 2 means this will be the suffix. So if you look at A, B, A, can 2 be there? No. Because 2 means 2 should be there, and this should be 2 and this should be same. So the suffix of length 2 should match a prefix of length 2, which is not. If it is 1, yes, suffix of length 1 matches with the prefix 1. So that's why we have a 1 here. We have a 1 here. Now look at the whole thing. A, B, A, B, A. Okay. Look at that. So from here, look at this position. From this here J, look at J minus 1. Okay, look at this position. Because if mismatch occurs here, you're going to look at this point. Now, if you look from this position onwards, backwards, what is the length of the longest prefix which is also a suffix, or the longest suffix which is also a prefix? See, AB is a suffix, it is a prefix also at this point. Okay. Now, I mean up to this point. Okay. So this will be 2. Now, if you go further, but there is no way to go further because we have reached the end of the string. We have to do only up to J minus 1. We have to compute the largest prefix up to only J minus 1. Okay. This is called the failure function, or also called the failure table. This is called the failure table. What does this mean? It means that if mismatch were to occur at a particular position J, where J is 5, then you have to go to the failure table for look for J minus 1. What is J minus 1? 4. Look for index 4. This is the failure happened at index 5. Suppose this mismatch with the given string happened at this position. That is, the mismatch occurred here at position 5. Then we know that because as of this position, there is a suffix of length 2 which is same as the prefix, then I can start the comparison with the string by skipping the prefix because it's already there in the suffix and this has matched. So I can say that I can start the matching from here because this is already deemed as match. It's already there in the suffix. So it's deemed as match. So I can skip all this matching earlier to this position. All the matching can be skipped in the pattern, and the matching can start from this position onwards because this is already there in the suffix. Right? This ABA. So now I'll start matching. If this is a position of mismatch, I'll start matching from here. So that is very important to know. Okay. Now, okay. So the crux of the game is to compute this array. How do you compute this array? That's not important. But if you compute this array, these are the values which you compute this array. How do you compute it? You start from the previous position, find out the longest suffix which is also a prefix. So for doing that, you can use, as somebody suggested, 2 pointers. So you can say pointer P1 and pointer P2. So go from that position backward and say, is this equal? Is this equal? Keep count. The moment it is unequal, take the count and put it here. Okay. Again, for every position, you have to carry what is the value. Okay. What is the value? So you have to compute that. Now I am hoping that you understood how to do this. Okay. Again, I am going to repeat this. I don't know whether I have some other pattern. Let's go to Geek for Geeks, pick up another pattern and try and understand this quickly. Okay. How to compute the failure matrix? The computing of the failure matrix is very crucial. Okay. So let's look at this pattern. Okay, let's try this pattern. Can you compute the failure matrix for this pattern starting from 0? So failure matrix of this. So let's say the pattern is AABA. So A, and remember, mismatch can happen anywhere. So if you take any position, let's start with this position. Okay, and if you see this and looking back, okay, if you see this and look back, what is there? B is there, A is there. Is there a prefix? Is there a suffix which is equal to the prefix? No. So we'll put a 0 here. Now look at just these two. Look at B backwards. So we have these two. If you see this, what is the longest suffix which is also a prefix? 1. So it is 1. And this is 0. Okay. Now if you take this position, okay, what will it be? We actually take only one position minus, but if we take this, okay, what will happen? This is AA, again it will be 1, okay, but we don't take that. So we take this, this will have only 3 elements because it is this position minus 1. The mismatch position can be at most 4 and therefore you need this value. So this is how it will happen. Okay. Now, okay. So how this will work is shown here, and you can look at that later. But this will be the pattern for this. Now, I don't know whether I have a better string for you to compute a pattern. Okay. Okay, let's take this string and compute its failure matrix. Okay. Yeah. So take this. Let's see how do you compute. So the pattern is AB, AB, AC. That is the pattern. So for this pattern, can you compute the failure matrix? Yeah. So this is 6. So the failure matrix will have only 5 values. Okay, let's see whether you can compute the failure matrix for this string, for this pattern string. AB, AB, AC. So AB, AB, AC, just remember. For that string, can anyone compute the failure matrix or failure array? Yeah. Try. The failure array, remember, to compute the failure array, you have to start from that position and take one position backward and check whether what is the largest suffix which is also a prefix. So can you compute the failure matrix for this pattern? Failure array. We call it failure table actually. So can you compute the failure table for AB, AB, AC? Let's see, anybody doing it. We'll wait. No, I haven't seen even a single guy so far. The failure table for this pattern. Okay. Okay. So this is how you do. Looks like you have inability to understand, but let me try. Okay. So the failure table for this looks like this. First, write the pattern at the top. AB, AB, AC. Write the pattern at the top. Now, for C, look at this position backwards. What is the biggest suffix which is also a prefix? Now you see, the suffix is A is there, so 1. But if you take suffix as BA, is BA there? No, BA is not there. So the longest string which is also a suffix here is only 1. Okay. Now look at B and then look backwards. Okay. So when you look backwards, is there in this string suffix is B and prefix is A? Does it match? No. So at that position itself 0. A, look backward. Is there a suffix which matches a prefix? Yes, so 1. Did I make a mistake? B, no, from here B, no, this prefix matches the
suffix.
Yeah, so I should, no, I think this is wrong. No, I think I made a small mistake. A, B, A, C. Now for this position it is 1. But if you look from this position backwards, there is this suffix. This is a suffix if you look from this backward, which is also a prefix. So this is 2. So at this position it is 2. Now look at this position backwards. This is a suffix which is also a prefix, it's 1. Then this is prefix, which is a suffix, 0. This is 0. So 0, 0, 2, 1. 0, 0, 1, 2, 1. Okay, so this is, you have to see what is the prefix which is also a suffix. So at this point, if you see, if you are A and look backward, this is the suffix which is also a prefix. So that's the length of that is 2. So I took that length as 2. Okay. So that is why I took this value. Okay. So this is the suffix which is also a prefix. Okay. Now, no, unless we get this, there's no point moving forward. So, okay, let's see if I can give you another pattern. Can you go to Wikipedia? Let's see if you have some patterns on Wikipedia. Just say Wikipedia KMP, because this is the key. If you know how to do this, then only we can proceed. Okay. Yeah. Yeah. So this is the original string, and the word is this, no? So he will give how to compute. Go down. There may be some. No, go down. Down. Keep going down. Description. No. Also known as failure table. Come down. Table building algorithm. Good. Go down. So, okay. Now, I think this is illustrative. Now the pattern is A, B, C, D and A, B, D. So let's just look at this pattern. A, B, C, D and A, B, D. Okay. Now, yeah. So now for D, what is the value we will store? So the value we will store for D is, you have to look from D backwards. See if there is a suffix which is also a prefix of this string from D backwards. This is the string. So if you look at this value will come as 2. Now you should understand why it came as 2. When you are at D, look backward. When you look backward, what is the suffix of the string backward? AB. Which is also a prefix. The length is 2. Length of the string, which is a suffix, which is also a prefix, is 2. So that is how 2 came. So I write 2 here. Now I am here. Okay. Look back. This will be from B. If you look back, that is from here. There is only A, which is a suffix and also a prefix. A is 1. So the next value will be 1. Now I am at A. Now look behind. D, is it a prefix? No. So 0. Okay. So under A, I will record 0. Then I go to D. Now skip D. D is the point of mismatch, let's say. I look at this. So is there a suffix which is also a prefix? No. So I'll record 0. Then 0. Then 0. Then 0. There is nothing matching. So this is what I will get. Okay. So the way he has recorded the failure, he has recorded -1s somewhere, but that is 0 is fine. And only 2. Now BD. Is this the pattern? No. This is the pattern.
Yes.
2. B is 0. A is -1. B. A was no here. The failure. Achha, this is saying how many steps he has to go back. Okay. Is he saying that? It's recording the number of steps. You have to go back. Now A, B, A. Look at B. This is 3. Yeah, this is 3. And A and A. Now he should put 1 here, not 0, not -1. I don't know what logic he is using to put -1. Now, if you see C, A, B, I think this also may make sense. Forget the -1s for a moment. A, B, A, C, A, B, A, B, C. Now, if you look at this, Now, I am at C, so I look behind and I have to fill up a value here. I think different people do it differently. So, what is the value I will put here? Now, if you look at from this position and look backward, so the value which is there is this is my suffix, okay, which is a prefix. Now B is not there as a prefix, so I should have a 0 here. For C, the value should be 0. I think this is recorded this way. This is 0. Then for B, okay, what should be the value? Now, if you look at B, you see this 3 and this 3. You see this is the same suffix which is also a prefix. So the value recorded against B should be 3. Should be 3. The value recorded against C should be nothing. B also nothing. But against B it should be 3, because if you look from B but don't take B, you will see there is a suffix which is also a prefix. Okay, so you have that. Then look at A. Here the value will be 1, which I think he will record it as -1. Okay, so we will record 1, because if you see from this position, we looked at B, we looked at A. We looked at B, so we got 3 because A, B, A and all that. Now we look at here, the value should be 2, okay, because if you look here, this suffix and this prefix are same, okay, if you look at here. So I got 2. Now I am at this position. Now I say A, I will get a 1, because 1 and 1 are same. I am looking at A, B, A, C, A. The suffix is A and A. Then if I go to A, then I look at C, it is 0. So I think all the earlier values you will get 0 as per our computation, our failure table. Okay. So this is how you compute the failure table. I don't know whether you have reached yet. Let's see some more strings where we can compute the failure table. We'll go to the chat, checking whether somebody has understood how to compute the failure table.
No, not one response.
No response. So we'll have to just stop. Go to the chat. Are you guys trying to understand how to compute the failure table? You have to look behind, find out the longest prefix, which is also the suffix. Prefix is the beginning, suffix is the ending. Okay, I'll give you one more example. Yeah. Now, the way they calibrate is different, but let's take one more example. Let's see how many respond. Otherwise, we'll stop. Okay. Okay. So let us talk about it. Okay, let's take another example. Let's see whether we have another example. Participate in parachute. Huh? That is the text. Take another failure table computation for KMP. Failure table for KMP. नहीं बाबा, don't go there. KMP बाबा. Let's see whether we have some examples there. No, at the beginning. Some string he has given. Okay. Again, same thing. AB. Let's see. How did he get 4? Okay, maybe, yeah.
Maybe down you can.
No, it's okay. Leave it. There is a. Okay. See, how do you compute for this? AB, A, B, C. Okay. So we compute for C. They list that as 0. Okay, because last value is listed as 0. They have different ways of listing. So C means you have to look at this backward. Okay. Now, if you see here, he's getting a value 4. I think you understand why 4. Because if you see the suffix AB, that is also there as a prefix. So you see, it can be common, doesn't matter. Right? So this is a prefix, this is a suffix. So its length is 4, so that's why he has a 4. Now, if you see the next portion, it is AB, A. He's looking at that now. Okay. So the starting value is 4. Now this is the next value. AB, A. You see here, this is a suffix which is also a prefix. So it is 3. So that's why he got 3. Now if you see AB, just this. This is a suffix which is also a prefix. So he got 2. Then he has ABA, prefix, suffix, which is also a prefix, only 1. All others earlier are 0. Okay. So that's how he computes. So this is called computing a failure table. Okay. Now let's do. I'll give you a string now. You give me the failure table for that. Okay. I'll give you a string X, Y, Z, W, X, Y, E.
Speak now.
Yeah?
It is coming.
Is it audible now?
No.
Huh?
It's coming.
Am I audible, guys?
Yes, sir.
It's audible. Okay. Now I was looking at another example. Okay. I had given you an example of 12.
1 minute. It's screen share.
Ah. Okay, I'll do screen sharing. Okay. Now watch my screen. Yeah. So I've given you a string, a pattern. Now can you compute the failure table of this? Try and compute the failure table of this. Starting backward. At least get some of the numbers right. Because unless you understand how to compute a failure table where the prefix and the suffix match, then only this algorithm can be understood. Anybody?
Yes.
I got this.
Huh?
We got it.
4 numbers.
Okay, some of you at least are struggling. Okay. Okay. Let's see how you get that. Okay, we'll go back. So you start here. Notionally we put 0 here. Go backward from here. Or you can put value here also. Depends. Generally we do j minus 1 where the j is the position of mismatch. So from here you see this is the suffix which is also a prefix. So I'll have 4. Then if you see this here, this is if you see from this position backward, it is 3. Then it becomes 2. Then it becomes 1. Now I am at A. I go backward. No, I am at X.
X is done.
Okay, X is X here. That's all. That means I am here. So I get 1. And now I am at A. So nothing. 0. I am at Z. So Z. Again I have 1, 2, 3. If you see here. So 3. If you are recording it along with that. Generally it is j minus 1. So that's okay. Then 2. Then 1. Okay. Again I am here. I am here. There is nothing. 0, 0, 0, 0. So something like this. So it is 0, 0, 0, 4 zeros, then 1, 2, 3, 0, 1, 2, 3, 4.
Same.
Let's see what you guys got.
Same.
They got correct. Okay.
They also got the same.
Okay. So this is the failure matrix. Now this is very useful, or this is the way KMP works. Now it's very easy. So now what will KMP do? Okay. Let us start. So now we will be given a string and we will have a pattern. So we have a string and we have a pattern. Now what we will do is pattern as a one-time activity, we will pre-compute the failure table. The failure table. Now what we will do? We'll start with, we'll use I as an index in J and J as an index in P. So we'll compare SI and PJ. Okay. We'll compare SI and PJ As long as they are equal, what we'll do? We'll say I plus plus j plus plus, as long as they are equal. Moment they are not equal, what we'll do? We will keep I where it is, okay, but j we will find out in the failure table the position, what is the value located at j minus 1. Okay. So suppose here the failure is here, what is the value located in the table at j minus 1? It is this, 4. So I will look at that position, see, it means that 4 characters are matched. So now whatever the value of j, I will not go back to the beginning. I can go 4 characters forward, because 4 characters are matched. So instead of starting at j equal to 0 again, I will start at j minus 1 plus failure of j minus 1. No, sorry. I'll start at I'll start comparing at failure of j minus 1. So failure of j minus 1 will indicate what? That how many suffixes there. So j minus that. So I'll start at j minus this f of j minus 1. I'll not start at j equal to 0 when there is a mismatch. I'll start at f of j minus 1. J minus f of j minus 1. That is, if there is a mismatch here, then it means, because the prefix and suffix are there, I can skip this and I can start matching from here. Okay, for the next position, I can start matching from here. For whatever I mismatch, I can start matching from here. I can skip this 4. So from j, I can go back, or start the matching at j is equal to. I can skip these. So I can say j is equal to f of j minus 1, something like that. I can start in. Instead of subtracting, actually I shouldn't subtract, because I can skip these many characters and start matching after that. Okay, so the pattern matching, I can skip that and start from there. So I can match from f of j minus 1, because all the earlier characters compared to that are already matched, because there is the suffix which is also a prefix. So I can start matching from here. So that is the beauty of it, that I can start matching. You may be j minus 1 or j equal to f of j minus 1, whatever. But this failure table will tell from which j I should start matching. Okay, so that will indicate from where I should start matching. Okay, so now let's look at the algorithm per se in the PPT and then in Geek for Geeks. Okay, so yeah, this is how the code looks like in Java. It can be in C++ or Java. So string is there, pattern is there. So text.length, pattern.length. Initially you have to compute the fail function. The fail array will be there. So the failure function has to be computed. You start with I equal to 0, j equal to 0. And then let's see how it goes to the next slide. Okay, so while I is less than n, obviously, if pattern at char at equal to j, and that is, there is a match. So sorry, this is when there is a match. If there is a match and j has reached m minus 1, that is 0 to m minus 1, then we can return the index. So Match has, that is the last character has matched.